Thank you. Hope you can hear me well. And by the way, we have pizza.
Yeah.
And I apologize. Math, at least for me, it's not the evening time. My brains work in the morning. So, but talking about math library without going into math, unfortunately, is impossible. So hopefully your brains are not as bad as mine at 7 p.m., but
there's some coffee, there's some caffeinated beverages if you want.
Yeah, maybe. Cool. And I've been passionate about math libraries for about 30 years. I'm in this business for all my career. I love mathematics from school. I, at some point, started programming, and I wanted to combine the things together. So this is how I ended up with math libraries. Historically, we started with math libraries for CPUs, and it was very different kinds of CPUs, including CPUs that do not have floating point arithmetic at all. So essentially emulated all floating point operations, and all math libraries about floating point. So at that time, my interests were in correctly rounded operations or emulating extended precision. Those who are old enough remember that Fortran, really nice language, has data type which is called real star 16, which assumes that you can do computations in 128-bit floating point arithmetic, and there is no hardware at all for 128-bit floating point. So one of my career projects was emulating 128-bit using narrow precision floating point arithmetic. So I've been in transcendental math library functions business for a long time. It was math libraries for everything. I've been with Intel at some point of my career, so I worked for MTL, and then Intel had Intel math kernel library and Intel integrated performance primitives, signal processing library, image processing library, and worked for math libraries for compilers. This is how Real 16 came. C compilers, different type of compilers, and at some point, obviously, GPU came to place, and general purpose computing started relevant on GPUs. So math libraries evolved to GPUs. So in the past, I would say 5 or more years, I've been focusing mostly on GPU aspect of math libraries, and this is how I started rethinking everything about math libraries, what math library really means running on GPUs. And I will try to share my thoughts about that, how it evolved over time. And this is kind of agenda, it's fact, but we are flexible today. It's just a conversation. Feel free to interrupt me at any moment and share your thoughts, ask questions. It's really informal. So at some point of career, and now I'm NVIDIA employee, so all my focus now is on GPUs and how to make math libraries running on GPUs. And because I was working on math libraries for Python for 10 plus or so years, I am happy to apply my Python experience now on NVIDIA CUDA and how to make math libraries at NVIDIA a little bit more pythonic, more consumable by Python community. So my present focus is NVMath library, which stands for NVIDIA Mathematical Library for Python. This is where I'm spending most of my time now, and I will tell you about my experiences with nvmath-python. Essentially, it's close to what I've been imagining, and now it's my ideas and ideas of many other people at NVIDIA, who are, by the way, many of you know them because they came from Python community. They are now helping to shape NVIDIA's vision of GPUs. So 2 years ago, we released our first version of nvmath-python, and one of typical questions was, guys, why are you inventing something new? We already have NumPy, we have QPy, we have Torch. We don't want anything else. So I wanted to start with exactly that point. So why are you doing that? And if you are in Python world and you have a fortune to maintain some Python project, you understand how much pain in maintenance. So Python is a nice language. It's nice productivity, nice usability for end user. But when it comes to maintainer, all this user pain typically is on maintainer. How to make end user life easy. So a lot of these pains exist is this irrespective of GPUs, but when it comes to GPU, the pains multiply many times. So, and because many of NVIDIA employees came from Python community and they understand all these pains, this is how we came to idea we need to reduce some of these pains by introducing so-called CUDA Python. And essentially, CUDA Python is an idea of getting Pythonic access to CUDA features. What if I need to initialize GPU or get information about GPU? What if I want to compile for GPU? Something like that, really lower level stuff. Or what if I want to find SO DLL where my CUDA toolkit is installed. All these typical pain points and maintenance burden, this is what we wanted to address in CUDA Python stack. So this is how it looks like. It's incomplete picture, but give you some idea what CUDA Python is. So first of all, how to get CUDA Python bindings to all these CUDA native library stacks. And they're typically low level enough, but still Pythonic. CUDA.core is more higher level APIs for accessing CUDA features. Pathfinder, I just mentioned, finding where certain library is installed. And it can be anywhere if you install with pip or install with conda or install with, it can be anywhere. So this tool is actually really great. It can find all typical installation locations. You don't need to worry about all that on your Python project site. And CUDA language, what I meant is compiling Python code. Number is obvious example. We all know number CUDA can compile Python code to GPUs. And you cannot do anything for GPU without compiler, right? Interpreters do not run on GPUs. So what you need either pre-compile, and you use native compiler stacks for ahead of time compilation, or you just-in-time compile and use something like number. Cool. So hopefully you understand the idea why CUDA Python was introduced, essentially to reduce pains for package maintainers like QPy or Torch. But also it has a value for really end users. I'm happy to use CUDA Pathfinder on my own projects. Cool. Yes, please.
This question, you said that for the other Pythons, is it its own, this the Python its own runtime, or is it something that works with other systems?
It's actually a native runtime stack, CUDA runtime stack, and CUDA compiler stack, like NVRTC. So it's native. Yeah.
So, I mean, obviously, I would expect it to work on NVIDIA GPUs, but would it work on like AMD's GPUs, or I guess
No.
Get it to run, or?
No, all our stack is primarily targeting NVIDIA GPUs. I will talk about CPU side a little bit, but for GPUs, it's NVIDIA only.
Thank you.
Okie dokie. So the same pains are actually, if you are a user of NVIDIA math libraries, your pain points actually multiply or actually grow exponentially. Because NVIDIA has 40 plus math libraries. So 40 plus at least SO files, so 40 plus TLLs. This is what you need to manage. Imagine a Torch contributor, a Torch maintainer, dealing with 40 different native dependencies. That's a pain. So one of value propositions why we decided that we need to bring really Pythonic math library is to reduce the pain of other package maintainers like Torch maintainers. Or Torch, maybe it's not a perfect example. Torch community is huge, but imagine the community of the project like QPy. Barely a few people working on QPy, and it's huge burden for them to maintain migration from CUDA 12 to CUDA 13 to CUDA. It's nightmare. Instead of focusing on feature development, they are spending time in migrating to the next version of CUDA. So one of ideas why we think that it's a good idea to introduce a new math library for GPUs is to get this burden on ourselves, so other projects can focus on their really the core part. So on top of CUDA Python, we introduce yet another layer. These are not 40 libraries, but these are representative examples. For example, I list here QBLAS. How many of you know that there are more than just one QBLAS? There is QBLAS, it's a legacy. You can think of a netlib type of library, netlib BLAS. But there is a QBLAS LT, there is QBLAS DX, there is a QBLAS MP. I forget, there can be some other QBLAS library. So behind this name BLAS or FFT, there are actually multiple libraries, and they're targeting different use cases. So all this craziness, we want to hide this craziness. I want to deal with something like matrix multiplication. I want to deal with FFT. I don't want to deal with matrix multiplication for this layout, for this GPU, for this use case. That's an idea why we really need even a higher level abstraction layer. Okay, And then again, nvmath-python, it's not only GPU library, it's also a CPU library. I'm listing here NVIDIA performance libraries, which is called NVPL in short. It's NVIDIA math library for ARM CPUs. But we also support x86. The idea is simple. No one starts development for GPU on GPU. It's nonsense. People start prototyping on CPUs, but then they realize this part of the code is suitable for GPU. I want to offload this to GPU. So this is how project typically evolves. So the idea behind nvmath-python, we are offering unified APIs to easily migrate from CPU development to GPU development or to hybrid development. With the same APIs, you can actually target both CPU and GPU and implement some complex cooperative workflows. Sounds great. I was hoping to show you some demo today. Magic demo. It will not run. I cannot connect to the labs system now. So you will probably satisfied with just slides. But this is a nice story. Maybe 6 months ago, it was last summer. It's more than 6 months ago. Last summer, I was playing with different implementations of matrix multiplications. I wanted to find some good story showcasing some advanced usages of matrix multiplication where traditional math libraries, they simply do not work well. And we all know such cases. There are certain users, especially in deep learning domain, they implement own GM-like kernels, matrix multiplication kernels, because traditional libraries do not work well for their use case. Matrices are either really small or kernel submission overheads are really high. So I wanted to find something like that, a simple use case. And I wanted to show that traditional approaches in traditional array libraries like CuPy or Torch, they don't work well for this use case. And the idea was, what if I use not traditional, really square matrices multiplication? What if I use so-called tall and skinny matrices? And the idea behind when you multiply tall and skinny matrices, original and cube complexity of matrix multiplication becomes close to linear complexity because you really have only one large dimension. And when you have linear complexity, it means that the amount of computation is linear compared to amount of reads and writes you need to do into memory. This is where inefficiencies come to place. We call this low arithmetic intensity. The number of reads and writes is large compared to the number of computes. This is why low arithmetic intensity. So I took two matrices and started implementing very simple use case, literally a few lines of the code in CuPy. I implemented it. I think I implemented first with operator notation, using add operator for matrix multiplication. I measured performance, but I wasn't satisfied because nvmath-python's APIs, they are more like functional form, mathmal form. So I thought before I start comparing with nvmath-python, it would be good if I do apple-to-apple comparison, mathmal versus mathmal. So I implemented second variant with CuPy. using matmul. And I measured performance, and I've got very different performance results. And I started scratching my head. Why is it so different? It's literally like 2 times, close to 2 times difference. It's not statistically insignificant, is what we call. And I didn't have good answer for a while. And I was even more confused when I literally used almost the same problem size. I just shuffled a little bit M and K. Theoretically, the amount of FMA, so flops, is the same. But I've got the opposite picture, really very different. So it was so confusing to me. And I spent a day scratching my head, asking around different people. I asked QPy maintainers, did they see anything like that? And end of this day, one of QPy developers actually gave me, and it may be related to operator at precedence relative to the star. You see? It's about broadcasting and the precedence. When we compute A at B with alpha, they have, apparently they have the same precedence according to Python rules. Which means alpha times A is computed first, then at B. It's not very logical for me as a mathematician, but this is how it happens in Python. And that's essentially the reason why all this happens. If you take a paper and pen and calculate the number of flops for this line and for this line, you will see dramatically different number of flops as a result. Cool. So, but then I also measured nvmath-python. Matmul versus QPy matmul, and the difference is again dramatically different. But at that time, I knew what exactly, because I found this example on purpose. I wanted to find this use case where really nvmath-python outperforms. And in my next part of this talk, I will explain what magic behind nvmath-python actually is that makes performance so different, despite the fact both QPy and nvmath-python rely on the same QBLAS. Cool. And I call this NVIDIA nvmath-python, which stands for ISO. Yeah. Cool. Well, in nvmath-python words, it really means compile, link, and perform. A lot of things that we do under the hood, math-wise, is associated with just-in-time compiling. There are multiple reasons. Again, just to run on GPU, you really need to compile. So if you pre-compile everything, which is fine, you end up with something like sitting on PyPI, which is more than 100 megabytes and actually close to several gigabytes. So when you pre-compile for different GPU generations, when you pre-compile for every single D type, you end up with several gigabytes of pre-compiled binary. When you compile just in time, you only compile for D type that you exactly need, for the mapping you need. So one of big advantages just in time compilation is just your footprint on PyPI, footprint or in memory, footprint in even compile time. So if I have a single message to deliver today, I would say that JIT is everywhere behind math libraries, and not only math libraries. This is one of fundamental technologies that we use now to get codes run really close. We call this to speed of light, close to top performance. And
For that, just in time, do you use Nova or do you have like a different thing? Like on
number is one of our core.
that's all I've seen.
Yeah. Yeah. We have some other tools.
It's called Nova. It's a lot better.
You can think of number, it's still the core technology. It's technology proven for many years. We use NVIDIA compiler stack under the hood of number, and it may be changing, but number, at least on user high level, this is core technology. This is not the only technology. For example, we announced qtile, which is tile programming. Unlike number, it's SymT programming, essentially per thread. We announced last summer on SciPy, I believe, we announced qtile, which is traditional block programming or tile programming. Really cool technology. It's simpler. It's closer to array programming of fixed block size arrays. So it's really nice. So it's more than number, but number is really core technology. Cool. Yes, please, one more question.
That you compile for the GPU. Is that you use that for that pre-compiled one? You moved it to the different operating systems still.
Well, you install on the target system. So target system has predefined operating system. So you don't have this problem. As soon as you install the package, we know the host environment, so we can compile according to that.
So if I'm controlling my hardware, is there any benefits to pre-compiling at this point, or is it just the normal, like I'm going to compile for this hardware, these are my operations, this is what I'm going to care about. So at that point, like if I have that level of control, then I can get around JIT, right?
JIT introduces significant compile time overheads. If you're sensitive to that, then pre-compiling is a good idea.
Okay.
Or you have homogeneous environment
Yeah.
you want to deploy, so you compile on one system and then deploy to multiple systems.
Okay.
Yep. Oh, so I will start with the most simplistic example. We call this host APIs. Traditional API, you run in typical interpreter mode, and from interpreter, you invoke a kernel submission to GPU. So it's really transparent. People don't need to know much about GPUs at all. Traditional programming model, very easy. A lot of people just start programming GPUs using that. So, and nvmath-python offers similar technology. I will explain the difference, why QPy may be not enough or Torch may be not enough, and you may want to use nvmath-python for that. And then we'll take a look at more advanced technologies. Again, the same example, implementation with QPy, implementation with nvmath-python. The only difference is the last line of the code. And APIs actually are very similar. On the surface, if you are looking, so what's the point? Why are you guys offering new API? We're happy with QPy. Well, on the surface, yes, APIs are similar, and they are similar on purpose. You don't want to learn programming matmul very differently from QPy, but we want to offer something unique that will make a difference. At least the whole idea, and we saw this on the very first example. Remember this, the precedence of operations. So obviously, QPy has different kernels. You can really change the order of these kernels using different techniques. And this is why you see very different performance in QPy. In nvmath-python, if you take a look at NC's profiler and what actually is a compiled kernel, you will see really just one kernel. So all these primitive operations, they are composed into a single fused operation. Because of just-in-time, I cannot say compiling. It's precompiled, but it's precompiled to IR, intermediate representation. So really, in late compilation stage, we have different IRs for different primitive operations, and we can fuse them depending on user choice. That's the essence of the technology. APIs are similar. Under the hood, it's the machinery for just-in-time linking of precompiled kernels. And the performance is, we saw this difference 3 times or so difference. Okay, it will not, you will not observe these differences if your matrices are square. Because in square matrices space, you have n cube complexity of gem. So this guy will dominate. You will spend most of your time in this kernel. So whatever order you choose, you still spend most of the time in this kernel. But for this use case, which is typical in machine learning, you have very few rows and vice versa. You have many rows and very few columns. That's the use case. Cool. Cool. The second example, it was inspired by my wife. My wife, she has a dog.
What's her dog?
It's my dog. And this is my wife's phone that took this picture. So the idea in image processing, you typically deal with some kernels doing either color transformations or some other type of transformations of your image. In this simplistic example, I take just one example, like Gaussian blue, and we implement this kernel with FFT-based convolution. In traditional approach, if you have NumPy-like API or SciPy-like API for FFT, so you first, okay, you have a separate function for doing convolution, but if you had FFT only kernel, then you first implement forward FFT, then apply in frequency domain some transformation, and then do backward FFT. This is how people typically do. And again, FFT is
Fast Fourier transform.
yes, fast Fourier transform. It has a n log n complexity. So it's non-linear, but close to linear complexity. So all these reads and writes make you paying. So like in our previous example, your ideal case, you want to fuse everything together. You want to minimize these reads and writes. You want to optimize your reads and writes by fusing all these iterations into a larger kernel. How to do that? Because convolution is just one of kernels. Users may have really custom code for implementing transformations. So we address this in the form of callbacks. Traditional way in QPy, you can add your custom callbacks, but these custom callbacks will be CUDA strings. So you really inject CUDA string, and you want QPy to consume your CUDA string and compile. This is not very Pythonic, right? So we really wanted to deliver Python experience. I want to write Python function, number one, and I want this function to be compiled and then fused into FFT. That's an idea. Again, that only works if I have Python compiler. So under the hood, we run number CUDA stack to get this compiled. Okay, that's an idea. And again, by implementing this sophisticated use case, we get significant dramatic performance gains. Yeah.
Do you turn that Python function and back into a CUDA string? Is that what you're doing? Or
Under the hood, it's compiled to, I'm not sure, into CUDA string. It's compiled directly to some IR, but yeah.
you're in the holy language?
Yeah.
Yeah.
Okay. And the last but not least example is, what if I really have completely custom code? And I was thinking about some good typical example that illustrates such a use case, and found that Monte Carlo is probably a perfect example. You don't need to be an expert in financial mathematics or in Monte Carlo at all. The idea is in Monte Carlo, you typically implement the past random. Yeah, you can think of random walk as an example. Typically, it's some stochastic process evolving in time. The only problem that this past generation typically involves very basic math operations, like plus, minus, exponentials, sine, cosine, random number, which is also very low cost operation. If you end up implementing something like that with QPy, it will not run perfectly, I would say. You can combine all these operations into and really make it array-like operations. The only problem with that, many of Monte Carlo algorithms, they are recursive formulas, so array operations are not always good. And second is when you do that, you need a lot of memory space, and Monte Carlo is very memory hungry typically. So in ideal case, you want to generate a single path, so you don't consume a lot of memory. But by doing that, you end up, you need really a compiler. You want these simple operations to be fused in something like a bigger kernel. This is why we use number, CUDA, or something like that. You really need to implement this logic. And all logic is just a few lines of code in compilable form. And actually, it works pretty well. The key point here, if you end up implementing a custom kernel, you need to implement basic math operations. In this case, it's just random number generator. You don't want to implement random number generator yourself. Or imagine in this kernel you call gem. You don't want to implement gem. It's very few people in the world can implement good gems or FFTs. So the whole idea, I want custom kernel, but I want the library to provide me APIs I can inject to do some basic math within my kernel. I want random numbers, I want gems, I want FFTs in these kernels. This is what nvmath-python provides really unique here. And the difference in performance, this little bar is what you get with QPy for obvious reasons. And if you implement this with number CUDA, this is how you get the best performance. Okay, hopefully you got an idea why JIT compilation is so important under the hood of nvmath-python. and different ways how we export this. Now let's talk about APIs. Why we do not follow QPy API or we do not follow Torch API? Well, one of the reasons we want fused operations to happen, so we really need our APIs to be accepting something that we can compose more complex operations from that. That's one difference. But the second difference, we want APIs to be so-called stateful. I will come to that in a moment. So let's take, again, matrix multiplication. And this is composite operation. It's not traditional gem, it's gem plus some activation function. If you're familiar with neural networks is gem, and on top of that is some activation function. In our case, we're using ReLU. So we want to combine gem and ReLU and fuse this into a single kernel. Okay, what happens behind scenes? The question? No? Okay. Behind scenes, actually, there are a lot of happening. You can enable Python login and see that we have something called specification phase. Then we have something called planning phase, and only at the very bottom we have execution phase. Single API call, but under the hood there is some machinery going on, and you can imagine some of this may consume cycles. CPU or GPU, it doesn't matter, it consumes cycles. And now imagine you have many small gems, which is not nonsense in many applications. Small gems in series. So you don't want to spend on planning or specification every single small gem call. My gems, they're really identical. Data is different, but shapes are identical. Why do I want to do replanning every time? So from that perspective, you want API that logically separates execution from planning, from auto-tuning. This is how you end up with an object state model, and we call this stateful APIs. So you have a state, and you implement different methods that implement different stages on that state. That's an idea. And this is how we can amortize this cost. This is traditional API, functional form, and this is how we can do with stateful APIs. Every single API in our library, it has both functional form for usability, simplicity, for quick prototyping. But when you end up in optimizing your workflow, you probably want to use something like
Think about it. Is it a different call to say stateful?
So it's you're literally calling, so it's a comparative, plan, execute, execute, but you're just telling it.
Yeah.
Okay. Can you replace operands? Okay.
This seems like computer architecture of discussions.
Yes. Yes, and imagine FFTs. FFT planning is really expensive. So you don't want to replan FFT every single call. So you need to implement something like caching. And this is one of ways how you can address that.
And it reoptimizes it. Like, local.
Yeah. And reset appearance, this is one of ways how you can essentially feed the next matrix. This is a type of API, but actually you can use in place operations. You can reset appearance in place. There are different ways how you can handle. I don't go into details here. Generic and specialized APIs. This is another big topic. it's debating and conflicting goals. Yes. One of our objectives is speed of light performance. We discussed that. The only reason why nvmath-python exists, it offers something that you can really use to get even better performance. We're talking about times, sometimes dozens of times better performance. So performance is one aspect, but performance comes at cost of productivity. So we want Python to stay Python. People use Python just because it's more productive than C++ or something like that. So
It's really hard to keep these people away from that.
we ended up offering two types of APIs. One we call specialized APIs. They may be exploiting very specific GPU features at the cost of portability or generality. But we still want to offer generic APIs for people to quickly prototype something. Or sometimes performance doesn't really matter much. I don't need specialized APIs for that. The best way to illustrate this on matrix multiplications. Specialized APIs. Imagine NVIDIA GPUs, they have so-called tensor cores. Tensor cores, they can handle tensor operations, but very specific shapes, layouts. So if you want to get the best performance out of hardware, you can only deal with these types of shapes and layouts, and you will really get the best performance. So this is where we call specialized matmuls. Matmuls with so many parameters. You can specify the tile, exactly how it maps onto hardware. If you're really crazy ninja programmer, you can do that. Oh, I don't mean you, I mean us.
No, it's like it's kind of funny, almost ironic. Like you want to do it, this is a specialized thing, but you can't. You don't want to do Python, right?
Yes.
Any comment on the specializations you're doing on what percentage of workloads are covered by those special cases?
Oh, there are many workflows, including very specific optimization paths in Torch, for example.
Like, well, I meant more like 20% of workloads where we can see special cases, or
I don't have this data, but you can imagine there are people who battle for every cycle of performance, and we want to offer to them a Pythonic way of doing things. They can still get close to native performance with Python. This is our point. And for them, we are offering these advanced APIs or specialized APIs. But for many people, we are offering generic enough. I want matmul, and I want matmul that takes matrix A, a dense matrix, matrix B, a sparse matrix, and I want results. So I want a vector and matrix. I want, I don't know, different shapes, whatever, generic APIs. The value in these APIs, sometimes they end up in different math libraries. Sparse ends up in Q sparse library, dense ends up in Q plus. People don't want to deal with all this mess. They want a single entry point. And this is what we call generic APIs. And there are something in between. I can illustrate it on FFT example. Remember this convolution example. In callbacks, you essentially compile Python function into IR and feed this as a callback to FFT. Unfortunately, it only works on GPU because our stack implements this fusion logic. It's applicable on GPU only. So in some sense, it's mostly generic, except if you're using callbacks, it will run on GPU only. It will not run on CPUs. And same with direct sparse solver. It's more on specialized APIs use case. In simple form, like solving AX equal B is generic enough, but it also provides advanced options, optional arguments. You can keyword arguments you can specify, and you can go as deep as close to bare metal as possible. Cool. We're close
I was
to
told
the
this was about Martin Luther King, I guess. Junior.
yeah, single domain. This is typical pain point. People, many, at least some of you come from HPC world. You at some point want to go beyond the single machine or single GPU, and that becomes a major project. We don't want this to be a major project. We want to prototype something on a single machine, on single GPU, and then with relatively minor modifications to get to multiple GPUs, and actually to a cluster. So many nodes with many GPUs. That's an idea. And the challenge here is that there's so many distributed frameworks or technologies. You have MPI for Phi, you have Task, you have Ray, you have whatever. So how to offer something composable? And by the way, one of our value proposition and the questions I typically ask, guys, you're offering something. Should I stop using Torch or QPy? No, of course not. We interoperate with everything. You can keep your application mainly written in Torch, but if you know some piece can run better with nvmath-python, nvmath-python works with Torch, works with QPy, works with NumPy, works with everything else. It follows array API standard. You can essentially do a lot of things zero copy. We accept all these type of tensors, and we are not in array library business. We are not implementing A plus B. We are not implementing element-wise iterations, broadcasting. If you're using nvmath-python, you still need array library to work with nvmath. You still need NumPy, you still need QPy or Torch tensors to work with nvmath-python. Okay. I forgot to mention this in the beginning. We are not reinventing the whole universe. We just want to be a good citizen in our common universe. Okay. So at the moment, and this is a big deal, we're offering distributed matmos and distributed FFTs. We currently support only MPI communication, and we're supporting Torch distributed. But Ray, Dask, it will come later. The whole idea behind this library, we actually don't need the specifics of particular technology. We can work with different communication or with different runtimes, but it's your responsibility to partition the data. So we are not a magical tool that auto-partition this. We let this business to do some other frameworks like Ray or Dask, or manually with MPI. We assume that data that comes to us already partitioned. But we take a major burden implementing all this algorithmic part, implementing distributed matmul or distributed FFT. That's the main pain point that we are addressing. So in this example, we are creating MPI communication. So process group, and then initialize. We support different backends, Nickel and Vishmem. We don't need to go into this level of detail. There are certain backends for MPI that are suitable for GPUs. Or Torch distributed. So single line change and everything else is the same. That's an idea. You don't need to learn programming Torch and then programming MPI. Everything within nvmath-python looks the same code. We do support very different data partitioning. That's another big deal. Imagine you have some large algorithm with some complex data partitioning. You probably want to be this business of repartitioning the data to be someone else paying. Okay, so that's an idea, and the very similar matmul. We saw this matmul 10 times already today. This is 11th time, but now this is distributed matmul. Cool. Performance. I don't have a good picture. The whole idea is dashed line. This is native library. Solid line. This is nvmath-python. You can barely see the difference. Essentially, performance is the same, which is not surprising. This is the scale limits. Probably the better talking point here is that we support really the range of data types. It's not traditional doubles in HPC. We're supporting AI data types, including FP8, scaled FP8, MX FP8, so-called, and soon FP4, all these crazy floating point data types I could never imagine in my beginning of career.
I've heard of the binary neural nets. They're really the 3 values coming out.
Exactly. That's the main use case. In classification, you don't need too many variants.
We can talk about
Yeah, we can talk. Yeah.
I think it's pretty beautiful in the app.
Okay. And the last but not least, this is something we literally announced this a few weeks ago. The sparsity. If you have an idea of the complexity of stuff that we are dealing with, abstractions of different libraries, of different layouts, different formats, sparsity, this is even bigger kind of worms. So when we are offering something unique here, I believe this is what that currently doesn't exist in QPy or Torch or any other Python library. And the idea here is traditionally you deal with what sparse library offers to you. And many libraries do not offer much to you. You want EOO or CSR. The problem is that my data doesn't fit well in CSR. I have different sparsity pattern. What do I do with that? So there are tons of inefficiencies in sparse domain that I want some custom sparse format that works for my particular sparsity patterns. So we want to go from common sparse formats like CSE to something like less common, not very frequently. You can find batch in Torch, but you cannot find batched CSR elsewhere. But the whole idea, what if I really want very custom format? So we want people to not deal with sparse memory representations. And we want them to be out of that business. We want to provide them some language where they can specify the sparsity patterns using that language. And then to implement operations on these unique sparsity format. So we don't want users to implement matmul for my novel sparsity format or solver. No. We want this to be actually doing some logic by dispatching to existing libraries or to compile some code targeting very specific data format. This is how I can say this, combined all ideas I described you earlier and put this into sparse domain. What we can do with JIT compilation, what we can do with callbacks, what we can do by leveraging all these libraries. That's really
You pick which one it is, or they define which,
which one? The format?
novel, yeah, if they have the novel case, is it done by the compiler? Is what I'm-
Yeah, it's done by DSL. Essentially, your only job is to specify, this is my format.
Yeah, where do you specify that? I guess?
Yeah. You specify the format, I do the rest. I provide implementation of matmul, solvers, and actually dispatch for best performance. And you will see performance numbers, it's impressive. So, high-level picture. It's zero-cost interoperability with other libraries. So, you can implement some of your workflows using CSR from CuPy or Torch or whatever else. It will work fine. With SciPy sparse, it will work fine. So we make these abstractions. We provide single API matmul solver. You don't have to deal with specificity of the format. You deal with matmuls. So it's polymorphic. Then I already described, you can really create custom formats. This is a language allowing to implement custom formats. It's based on PhD work of, which is 30 years old. And this person, he wrote this PhD 30 years ago, and most of his career, he was working on something else, but then MIT, I believe, they took this idea, and his PhD was about matrices, and MIT, they expanded this idea to general tensors. So they call this TACO. And then TACO became, to some extent, very popular. So we decided, what if we take this TACO idea and now bring it to Python world? That's an idea. TACO is C++. Okay, we can actually inject even in Torch model. I don't have time today to show a demo, but you can create a universal sparse tensor from nvmath-python and inject into Torch model. And Torch model, without any other changes, will run magically significantly faster. That's crazy stuff. And again, a lot of this is based on JIT compilation, LTO, and we do caching of these kernels without.
Top left, when you say zero cost, you mean developer implementation?
Oh, zero copy, I would say. Zero copy.
So speed, no speed cost. Okay.
Yeah. But also from developer perspective, I don't force you to rewrite everything.
Figure it out.
Yeah.
Okay.
A very simple idea how we integrate. So we create tensor using just SciPy sparse. So we created CO, and then we convert this SciPy CO to UST, and this is zero cost. This is what I did. And then you can, after that, you can do all this magic. You can do LTO, just-in-time compilation. All this magic becomes to work after this conversion. This is an example where you define truly unique data format representation, which is called delta format. I don't have time going into detail. The whole idea, it's not supported by any other library, and it is really good for certain deep learning models. We
The deep learning, someone, the company who does this come to you guys, or you just did it because you get it?
I wasn't involved deeply, but that person who wrote this PhD, he was in touch. And actually, they gave us some good use cases, gave it an idea of this. So some useful utility functions, you want to actually print information of your tensor and have different ways. I want to print the matrix, so I want to print the storage, or I want just to see the full structure. Okay, this is an example of polymorphic operations and how the dispatching works. And this is an example of torch injection. I was telling, the demo was actually nice. We ran like 50 torch classification models for image classification with injection and without injection. The performance is dramatically different. Okay, I'm sorry. And this is the performance numbers. The whole point, those who are familiar with QPy supports CSR really nicely. It's performing well. It's essentially backed by QSparse library. So the problem is QSparse library supports CSR only. So QPy being close to NumPy also supports COO, DIA formats. Because QSparse doesn't support these formats, what QPy does, it essentially converts to CSR and then back to COO, back to DIA. You can imagine it's huge memory footprint if you have huge matrix, and it's also very slow. Essentially, all these blue numbers, they are very slow just because in COO or DIA, QPy just converts this to CSR. With Torch, situation is, I can say, similar. For example, Torch doesn't support DIA at all, and COO performance is horrible too. Exactly for the same reason, there is no QSparse support for COO. What UST provides, these LTO implementations, so it's compiled code, and it's performing really, really nicely. CSR, this is precompiled QSparse. COO and DA, this is just-in-time compiled performance. And they're really close. That's the magic. So the really hope is with something like UST, we can easily help QPy or Torch developers to close these gaps. Yes, please.
So I was this here. I would DIA be most, I guess, efficient. Would be the most efficient one, I guess.
Yeah.
Does this runtime include JIT?
No, it does not include JIT. It just includes execution time. So, yeah. And we are close to the conclusions. Like I said, we've been in this journey for 2 years. Literally 2 years ago in March, we had prototype presented on GTC conference, and 2 years later, we covered so many things, and we really hope that projects like QPy, like Torch, and any other Python project can leverage all this goodness of CUDA-Python and nvmath-python to really focus on what they want to focus on, and not on getting last bit of performance of C or last bit of performance, or managing this CUDA path installation.
You mentioned before that only some of the advanced things are available on CPUs. Is UST available on CPU?
UST, yes, UST is available on CPU. And it's very new. We currently have limited support for matrix, SPMM, essentially operations, but we will expand into other matrix operations and linear solvers eventually.
So can you become a dependency of PyTorch and GPy in the future, or they keep their stuff?
With QPy, the answer is much easier. We're already working on that. You can actually see RFC open to make nvmath-python a dependency of QPy. It's already in progress. With Torch, the situation is more difficult because they're currently exposing math libraries on C++ level, and it's up to them if they want to continue managing this pain on C++ level, or they want to go up level with Python stack.
Is PyTorch still only NVIDIA?
Oh no, PyTorch runs everywhere, on CPUs, on all kind of GPUs.
So they might not want to be part of it.
Yeah. So I cannot speak for them. I can imagine it will be more difficult choice for them. Yeah.
So to piggyback off of George's question, which you may want to talk about later. So I don't have an endless supply of money, but NVIDIA of course does. So, I would, if I was going to, NVIDIA or a large company was going to run an operation, say like on Amazon, you would get a dedicated machine. I would go more for, I forget the term they use, but the one where you in the spot market.
Yeah.
Yeah. So then I'm not exactly sure how it would get handled, but at some point you could get interrupted and then you could maybe move to another machine.
Mm-hmm.
So at that point you would somehow indicate that you could be going to a different architecture, because you were talking about a one-time chip, right?
Yes. Yeah.
So can you manually say, I've moved, you need to handle yourself, or do you kind of have to start over the operation? Does my question make sense?
What I know, this is the stack from CUDA-Python, so I'm not exactly sure about details. What I know, they're really working on GTeam side, and especially focusing on ahead of time compilation to address all of these use cases you just mentioned. I'm just not the best person to answer this.
Okay,
I think it depends on how you as your as a software developer might have to manage that a bit.
yeah, I think so. But
Like we have spot instances. The spot instances right now have been they've been just getting ripped away from us, because everyone, the compute right now is limited. So they just pull them away. They don't even give us a new one back. So that case.
I mean, hopefully you can complete a cycle and
Well, you'd have to say, if you wanted to complete a cycle, you'd have to save that state somewhere.
yeah, and then start over from the state.
Start from that state. And
Yeah,
that's,
yeah,
that's
okay.
a lot.
Mhm.
But yeah, I think you would have to build that. Or maybe your cloud provider possibly do that, and I don't know. I don't know how Kubernetes does it, where they do like auto scaling, like they'll auto scale you horizontally, vertically, so they give you like another computer. But
That's not true.
yeah, yeah.
Basically, it says all people auto scale. Say something, but that's not. It's another one.
Yeah,
That's.
yeah. So yeah, it's pretty.
Yes, please.
For the about visualizations, is there like a standard? Is there like a default format that it outputs? So
Debug visualization, like this one.
no. I think there was one where you're showing actually where it was able to actually get a visualization of the tensor.
Oh, visualization of a tensor. Visualize it like this one. Okay.
Is that so? When you actually call it, does it actually output a file or something like that? Or
It uses matplotlib, so you can do image output if you want. Yeah. Not sure, not matplotlib, pillow like this. Yeah. Yeah. Thank you guys so much.
I have a question here. Can you hear me over there?
Yes.
So actually two questions. First one is, why did you choose the Apache license? This is the first question. The second question is like, how much, I understand that you did math, but one of the things that are missing actually from GPU, from like running on GPUs are statistical functions. What can you do with this?
Okay. That's a good question. The only statistical part as of now is random number generation. What I can tell you, we have some of statistical functionality covered in Rapids, in pandas like computation, but this is really basic statistics. A couple of months ago, we were given a talk jointly with Probable, which is scikit-learn maintainers. For scikit-learn, their path to GPUs is through array APIs. So essentially, they're relying on data APIs for getting to GPUs. So they're covering some of the statistical part also. And in general, if the library, statistical library, I'm not sure, stat models should actually work on GPUs, I guess. Technically, I never tried it. But the problem is NVIDIA doesn't have native libraries for statistical computing. There is nothing to offer on Python and that's the short answer. And your first question was Apache versus we are currently BSD. I don't know. It was broad decision for all Python stack, including CudaPython, to be Apache or BSD. I'm confused now. I think it's Apache.
Yeah, I checked. It's Apache. I was wondering because I was looking for statistical libraries of specific capabilities and licenses that can run on a GPU. I had to write one for by myself, not by myself, meaning I had to patch everything, and I made it only from public domain elements. So it's possible to release it into public domain at all. So the question is, why is the license then?
Oh, I don't know. I don't have this answer. I saw Katrina is on the call. I don't know if she.
Yeah, Katrina had a problem with licenses several years ago. Let's not go there. She couldn't figure out when I was asking questions. Now she has to deal with it. Now she's on the call and she has to deal with it, because you can do those things public domain if you want to. The question is, do you want to? And if you don't want to, why not? But that's a different question for a different time and space.
Yeah.
but the statistical thing is something that's missing on GPUs. But it's possible to do it public domain. But let's keep it at this point. It was a very interesting talk. Thank you.
Yes, sure. Thank you, and good questions.
So one thing is you have all these underlying libraries. So this is the Python. Any other languages? Is there NVM math-language?
I'm pretty sure, at least on the compiler side, we are going well beyond Python and C++. The problem.
My question was going to be: is there an
yes,
NVM
the
math
problem
class?
with NVIDIA, there are so many projects. So there are some projects. If the question, are they going to be live in production anytime soon? I have no idea. But definitely there are tons of languages NVIDIA is working on. Cool. Thank you, guys.
That's
Yeah.
really
Definitely tell
excellent.
some of my friends about it.
One more question, if possible.
Yes, please.
Thanks for the good presentation, by the way. My question more about performance of the library itself. Did you make any comparison with the competitors, any of them, like AMD, Intel, whatever? Do you plan anything like that in the future?
The answer, no, we did not compare AMD and Intel. We are actually, I'm a little bit easy business. I'm Python guy, and my speed of light is respective C++ native library. I leave these comparisons to them. So if they care about comparing Intel or AMD, it should be their business. I'm not optimizing much for specific. My primary goal is to provide pythonic APIs to native libraries, and their business is to optimize these libraries for great performance.
Okay, it's more about simplification of operations instead of just performance and so on. But yeah, I'm just interested in general to understand how it will be with the larger frameworks, because performance you demonstrated today is a great, but it's just a performance on the operations, not just something global. Let's say if to take the NP bench framework, what the results will be. Just interested.
No, these are all valid questions. You're right. I was probably too bold saying that I leave the performance question to native libraries, which is not completely true. We care about performance, but we essentially minimize several things. We minimize interpreter overheads. This is our goals. And we have some ways of doing that. We can do something on Python side. We can go to Cython. We can go to Number compiled codes. And second, we care about JIT compile time overheads. And this is where we work with Number team to minimize that.
Yeah, and this is very great work. Thank you for presentation once again.
Yeah, sure. Thank you.